All right, y'all. So welcome to Energy and Heat Part 1. This first part's going to be mostly conceptual. The second part's going to be more mathematical. So for this first thing, I just want to talk about, well, we know what energy is. We can generally define it with potential energy or kinetic energy, but heat is a very general term, and we kind of think of adding heat as increasing temperature. But if we take that a little further, temperature is nothing but the average kinetic energy of a system. So in a weird way, we're calling this unit energy and energy. But for the purposes, we're just going to be talking about energy as one thing and heat as another. Generally, when we talk about energy, we're talking about like the energy of the entire system, while when we're talking about heat, we're talking about average kinetic energy. So here we'll generally be talking about total energy, and we'll probably be talking about kinetic energy over there. So with that out of the way, we need to kind of move back a little bit to what we remember about solids, liquids, and gases. And actually spread these out a little bit. And if we have a container containing a solid, might have just been faster to draw this twice. But if we have a container containing a solid, a liquid, and a gas, particles flying all over the place, we generally think of the energy as increasing. So as we go from solid to liquid, we have increasing. And specifically, we think about kinetic energy, increasing kinetic energy, because kinetic energy is the energy of motion, increasing kinetic energy or motion. And same thing, increasing kinetic energy, maybe motion. And this is a really important idea because the particles start from being very close and just kind of like vibrating together to starting to kind of move around each other nice and easy. And then finally in gases, all the particles are individually and moving on their own, flying in all different directions. And with this, it takes energy. It takes energy to loosen the bonds between the atoms, and it takes energy to completely break those bonds. In fact, when we're looking at this, the specific energy it takes is called the heat of fusion. And that's, oh, sorry, heat of fusion. And that's going to be the, I'll switch colors, energy needed to go from solid to liquid. And then next, we also have the heat of vaporization. That's going to be the energy needed to go from liquid to gas. Now, it takes a considerable amount more energy to go from liquid to gas and solid to liquid, because as we move from solid to liquid, we're only kind of loosening those bonds. The particles don't have to break off completely. They just kind of have to be able to move a little bit more. But as we go from liquid to gas, these particles are free and individual and flying everywhere. So they need a lot of energy. So the heat of vaporization is usually much higher. All right. So what we're going to do is we're going to kind of look at water, and specifically the way we generally talk about heat and energy is we look at the heating curve of water. Now, that's kind of a misnomer considering that in our heating curve of water, we don't really have curves. We're mostly going to be dealing with straight lines. Whoop, too much. And as we look at this heating curve of water, we have a couple distinct sections, namely 5. We have these 2 horizontal sections, and we have these 1, 2, 3 vertical or diagonal sections. Furthermore, this is a graph, so we need some axes. Well, on the y-axis, we'll talk about temperature. And in this case, we're going to use degrees Celsius, and we're going to make some points at 100 degrees Celsius and at 0 degrees Celsius. So notice that's the boiling and freezing point of water. On our x-axis, we're going to be talking about the energy. And this is the total energy we're adding to the system. So what the heck does this whole curve mean? Well, let's talk about it. In our diagonal sections, usually what we're saying is we are heating the water, but not changing the state of matter. So in our 3 sections, first in our bottom section, we have ice because it's below 0 degrees Celsius, below the freezing point of water. So in this section, as we add energy into our system right here, all we're doing is heating the ice. Maybe the ice went from -20 to -10 degrees Celsius right there. So when we add the energy, it's still very cold, but it's not yet hit 0. In our next section, we have liquid water. And again, in this section, we're just heating it up. So maybe we have room temperature water at 25 degrees Celsius. We want to make our coffee at 80 degrees Celsius. So really, we'll just be adding energy, which will go to heating it up. And in our last section, we have our gas. Again, the gas just gets hotter and hotter and hotter. So if we have our solid, our liquid, and gas, the question then becomes what's happening at these 2 horizontal points? Well, at our horizontal points, what we're doing is we have phase changes. And in these phase changes, we'll have both states at once. So right here, we'll have ice and liquid water. And up here, we'll have liquid water and what we actually refer to as water vapor. I'll go ahead and write that over here, gas, water vapor. So in these scenarios, we go from heating. So right now we're heating a solid. Then it reaches a certain point where all the energy we put in, instead of increasing the temperature, because this is flat, it actually says we're putting in all that energy to change from the solid to the liquid. Once that's done, we're just heating liquid water. And then once we hit boiling at 100 degrees Celsius, every extra bit of energy is turning the liquid water into the gas, at which point that just heats up. So to make this a little more direct, let's make sure we can see that our points are at the boiling and freezing point. And this is a really special way to look at it. Something that you might think about when you're at a restaurant and you have a glass of water is, if you've got your glass of water and you've got some ice cubes in it, and you leave your glass of water for about, let's say 20 minutes, and you still have some ice cubes, but they're a lot smaller. Now, if we assume that our water initially was 0 degrees Celsius, and we have both liquid and solid, we have our liquid and our solid, then we're probably at 0 degrees Celsius. We're probably at this range in our curve. Even though we leave it and it's exposed and the ice is melting, we still have our solid and liquid. Therefore, we're still in this field. So we know that even though we left our cup of ice water out for 20 minutes, because the solid ice is still there, we know the temperature of that water is still going to be 0 degrees Celsius. So the last thing I want to do before I end this is just kind of lead us off into the math. In our diagonal portions of the graph, we're going to be using an equation, Q equals mc delta T. And in our horizontal portions of the graph, we're going to be using an equation that's Q equals m delta H. Now, this first equation just says it's mass times heat capacity, which we'll talk about, times the change in temperature. This equation is just mass times the heat of vaporization or fusion, depending on whether we're going from solid to liquid or liquid to gas. And this H, lastly, finally, actually means our change in enthalpy. But for now, don't worry about that because we'll get to it next class. And as for enthalpy, this is the only time you'll ever hear that, so don't worry about it. So I'll see you in the next video where we'll be doing some math. Have a great night. Bye.